Okay, not quite sure why, but right. Now here for the for the non-deterministic Turing machine, well, as Sipser gives anyway, for non-determinism, it's only left or right. There's no S in there, big S. S for stationary, stay put. That's not included. I'm not quite sure why, but yeah. Anyway, all right. So each time you get a non-determinism, when you get choices of what you could get a choice in the next stage, you could get a choice in what gets written over by the head, and you get a choice of what the next move is. So any of those possibilities, or combinations of those possibilities, then you have non-determinism. Okay, so I hope that's clear. Then it's a broader definition of non-determinism for a Turing machine than it is for a finite automaton. Okay? So you'll need to modify your transition function to this. So all that's the same. And remember, when you have non-determinism, this P here is the power set. Remember the definition of a power set? The power set of a set A is the set of all subsets of set A. Okay? Because what you'll get here is you can have a whole set of possible triples. A state, a symbol to be written, and a move. You can have a whole set of triples because it's non-deterministic. If you only have one triple that gets returned by the transition function, well, then it's a determinist. Right? If it's always just one, if there's 0 cases of more than one triple being returned by the transition function, well, then it's a determinist because there's no choice about what your next step will be. Okay. All right. So I hope that's fairly clear now of what non-determinism means for a Turing machine. Okay. And the computation of a non-deterministic Turing machine, again, will just be a tree, and every time you get a branching, you'll get a. Well, say there are like 2 ordered triples that get returned by the for a given current state and what's being read by the head. For that ordered pair, let's say there are 2 ordered triples returned. So that's non-determinism. You now have a choice. You can have 2 different steps, and so you get a branching in your computational tree. You get a branching, and you'll make a copy. You'll have now 2 copies, 2 children from the node, and 2 Turing machines. And one of them will have the configuration, one of those triples, and the other copy of the Turing machine will have the other configuration, the second triple, a next state, a symbol to be written, and a move. Okay, and then those 2 Turing machines will just independently proceed. They'll just go down their various branches, and they may split again and again, and you get a whole tree. Okay. Right. So that's so the splitting of the tree into more and more branches. That's familiar. That's really no different from what you've done before. So that should be fairly familiar. Okay. All right. Well, now so the next thing we'll do is we will now prove that a non-deterministic Turing machine has an equivalent deterministic Turing machine. In other words, has the same power. So we'll start on that, and it continues. So 1, 2, 3, 4 squares. So two full sessions. rather long proof. Okay? So here's the theorem statement, as I mentioned a bit before. So effectively, you might think, now, I mentioned it before, it's not obvious in some ways. Like, think about, because it goes both ways. You can argue both ways. In the case of the finite, as I was saying a bit earlier, in the case of the finite automaton, the non-deterministic finite automaton is equivalent to the deterministic finite automaton. The DFA and the NFA, they're equivalent. They have the same power. Whereas for the PDA, the push-down automaton, the non-deterministic PDA is actually more powerful than the deterministic PDA. So that's the opposite. It's contrary. So now we're dealing with our third major model of an automaton, a Turing machine. So which way will it go? Is the non-deterministic form of a Turing machine, will that be more powerful? Can it recognize a greater class of languages than the deterministic form? It's not obvious. I mean, you've got precedents going either way in the past, right? The DFA is equivalent to an NFA. Oh, sorry, the other way around. Well, it doesn't matter. In the PDA case, the non-deterministic PDA is more powerful than the deterministic PDA. And so let's settle the issue for Turing machines, because this is really important, because Turing machines are equivalent to virtually any computer. So in that sense, there's a lot at stake here now, right? If it could be shown that a non-deterministic finite automaton was more powerful than the deterministic, if a non-deterministic Turing machine was proven to be more powerful than a deterministic Turing machine, that would have real consequences, right? Then people would be designing the equivalent of non-deterministic machines because they would get more power. So there's a lot at stake. I mean, this is not just math, right? If it were the contrary, if an NTM and a DTM, a non-deterministic Turing machine and a deterministic Turing machine, if an NTM and a DTM were not equivalent, that would have profound consequences in terms of the real world and power of computers and stuff like that. Okay, so this particular theorem is important. Okay, so it's effectively just saying that NTMs and DTMs are equivalent. Well, put it this way, more precisely, every NTM has an equivalent DTM. Right? You're given an NTM, and you can find an equivalent DTM. You can construct it. You can build it. So it's a proof by construction. Okay, effectively. All right. So how to prove this? Well, again, just